Q fever is an illness caused by the bacteria called Coxiella burnetii. This graph presents a clear spike in the illness through the periods of 2007 through to 2009 in the Netherlands. This outbreak was thought to have been caused by the exposure of the bacteria-contaminated dust particles, which would have originated from infected dairy goat farms affected by abortion storms. René van der Brom and a team of scientists researched the spike of Q fever cases and its relevance to the infected dust particles from goat farms. Van der Brom and her team had two goals. The first was to clarify the role of Coxiella burnetii contaminated manure and the transmission to humans, and the second was to assess the impact of storage on temperature profiles of manure piles. In the Netherlands, farmers must register the transport of manure from their goat farms to its destination. Van der Brom used these records and compared them using descriptive statistics and binomial regression models. This model represents the dairy goat farms, red dots representing farms with reported abortion storms, green dots representing farms with no reported abortion storms, and the blue zones representing reported cases of human Q fever illness. It can be obviously seen from this figure that the higher cases of Q fever occur in areas surrounded by farms with reported abortion storms, although the results for the binomial regression showed no association between the incidences of human Q fever cases and the origin of the manure, as well as finding that there is no association with the amount of manure distributed. For the scientists to estimate the temperature profiles between the shell and the core measurements, they set up three equations. The first presents the conductive heat transfer according to Fourier's law of heat conduction. The second is the first equation solved for the differential equation and shows the temperature within the dunghill varies with radius. The final equation is the second equation simplified, and this equation was the one that was used to calculate the temperature profiles. The results of the temperature profiles can be seen on the graph presented. It can be clearly seen that the case which includes heat production inside the manure pile shows higher temperature values across the entire range when compared to the cases with only heat conditions. The results showed that the temperatures in the core was less than those of the shell. This would most likely be the result of successful composting. The results show that at least 85% of segments would be highly likely for any C. burnetii to survive the composting process. It suggests in previous studies that manure remnants had a large impact on the transmission of C. burnetii to humans. Although the results from this study present no relation was found between the distribution of goat manure and the transmission of Q fever virus to humans. This also applied for the epidemiological risk factor studies. Although large amounts of C. burnetii were found in samples of it could not be cultured. If viable C. burnetii were found, composting it would have had a large effect on the spread of Q fever. So it can therefore be concluded by the study that land-applied goat manure most likely played a minor role in the outbreak of Q fever, and that it could potentially be to the use of incorrect composting processes.